So, good afternoon, students. So today we will going to start about the next topic for your JAM economics paper. Okay. So today we will cover the mathematical statistics part of this of JAM syllabus, that is mathematical statistics. So in this portion we will cover about random sampling, type of sampling, point and interval estimation, then after we will cover properties of estimator, okay, sampling distribution, confidence interval, then we have central limit theorem, and law of large number, and the last part is estimation of population parameters using method of moments and MLE, that is maximum likelihood estimation. So this is a part of your statistical inference. Okay, this is all these are the part of your statistical inference. Okay, so I will start by random sampling, type of sampling. Okay, so it's okay, start. So first of all is like, what is random sampling? Okay, so random sampling. So random sampling means selecting unit from a population. Okay, so first of all you should know what is population. So for example, suppose you have a class of 100 students. So these 100 student is a population, and you have to calculate the mean height. Okay, suppose we have to calculate the mean height of the class students. Okay, so you don't have that much time to just measure the height of all these students, all the 100 students. Okay, because it is very time consuming. So what you have to do, so you randomly select the 10 students. Okay, so these 10 students selected in such a way that these students selected in such a way so that these 10 students represent 100 students. Okay, so we will select these 10 students in such a way that these represent the 100 student. So these 10 student is what we known as, this is your sample. Okay, so for example, this is, suppose this is a population, and in population you select some smaller value, and it is your sample, and a sample is a representation of the population. Sample is representation of population. Okay, so this is a difference between sample and the population. So what is random sampling? So random sampling means selecting units from a population such that every unit has an equal and known chance of being selected. Means, for example, in these 100 students, you select 10 students, so that so the probability of each student should be equal. Not like you are select the first student with the probability of 1 by 10 and another student with the probability of 2 by 10. No, the selection probability of each student should be equal. Okay. Now, why random sampling is important? Like someone asked that why it is important. We can just select first 5, 6. Okay. So why random sampling is important? Okay. First of all, it makes the sample representative that I have discussed this earlier. Then after, reduce selection bias. What is selection bias? For example, suppose that you have a group of 10 people, okay, and your teacher has just selected one student as a captain, but he have to select 5 students for the cricket match. So what he done, he just randomly just selecting his all 5 best friend, or suppose he select the 5 friends and leave the another 5. So that is what is selection bias. Okay, then it's allow valid statistical inference. In the upcoming classes, we will see how these samples are used to estimate the population's parameters. Okay, now we will see the types of sampling. How many types of samplings are? Types of sampling. So types of sampling, we have the 2 types of sampling. First is probability sampling, and the second is non-probability sampling. Okay. So first of all, is probability sampling. So what is probability sampling? So in probability sampling, each unit has a known non-zero probability of selection. Means in each unit, like for example, each 100 student have the known and non-zero probability of selection. Okay, so there are many types of probability sampling. That is like, first, let me change some color. Like first is simple random sampling. SRS means, what does it mean? It's mean that every unit has equal probability of selection. Okay. Then the second is stratified sampling. Stratified random sampling. And yeah, in simple random sampling we have the two. And what are the two? Is with replacement and without replacement. So what is with replacement? So with replacements mean ki, like, for suppose you have the 3 balls and you have to choose one. So with replacement you can first choose the one and then keep that ball in a box and then after again choose one ball. Okay, but in without sampling you have to select one ball from the box and just keep the ball away, and in from the left balls you have to select the another ball. Okay, so what is stratified random sampling? So stratified random sampling, population is divided into homogeneous group, which we known as strata, and then random samples are drawn from each stratum. Okay, let me explain this. Suppose you have a population. You have a male, female, and children. Okay, so in stratified random sampling, it is a stratified random sampling. What you will do? You will make the strata where it only contain male population, it contain female population, and it contain children population, and you draw the sample from these students. For example, you draw 5 male population, 5 female population, and 5 children population. And why we need this stratified random sampling? Because suppose in simple random sampling, say you have 100 individuals, 100 adults, and in 100 adults you have 60 male and 40 females, and you have to draw suppose 10 adults. So in 10 adults what will happen? It will be possible that in 10 8 are male and 4 are female. So this is not the correct representation of the population. That's why we use the stratified random sampling, because here we divide the whole population in a homogeneous group and then select samples from the each stratum. Okay. And the third is what? And the third is simple systematic sampling. So what we do in systematic sampling? So systematic sampling, we select every kth unit after a random start. Okay. Okay, let me explain this. For suppose you have a queue. One person is here, one person is here, and dot isn't in here. Suppose we have thousands people standing in a line. Okay, so in systematic sampling we select a kth unit after random start. For example, we start with k is equal to 2. Okay, so we select this pair. So after that we will select every 2 persons. Okay, see, like we have select k2, then after we select sorry, this will not, sorry, where is it? Oh, sorry. So after every 2th person we will calculate. For example, see, okay, so we have select 2. So after that 2, 1, 2, we will select this. Then after we will select these. So in systematic sampling we select every k unit after the random start. You can start, like you can say instead of 2 you can take 3, you can take 10, you can take 11, any unit you can do. Okay, then you have a cluster sampling. So what we do in cluster sampling? In cluster sampling, population is divided into clusters, and some clusters are randomly selected. Okay, here I can give the example of customer segmentation. Okay, for example, suppose you have a credit card data. Okay, let's suppose credit card data. So here you can see some people spend more than 10,000 monthly, some spend more than 50,000, and some spend more than 90,000. Okay, so you can see these are clusters. Okay, and in clusters you can select some clusters randomly. For example, they have 3 clusters, so we select this cluster as randomly. We can select this cluster as randomly, and it is not like that you have to divide clusters in 3. You can divide in much more, like you can divide a cluster in different criteria. Okay, like spend less than 5,000, okay, then more than 10,000, more than 50,000, like this. You can divide the population in a clusters, and in clusters it contain male, female, it also contain male, female. Okay, so this is cluster sampling. Okay, then it's come non-probability sampling. So what is non-probability sampling? Non-probability means like selection probability is unknown. Okay, what does it mean? Like, for example, you have a group of 10 and you have to select 5 students, and you just select 1, 2, 3, 4, 5 come. There is a no equal probability of selection, or the selection probability is not known. So what are some of the sampling techniques? So some sampling techniques are convenience sampling, like you choose that sampling method that is very convenient to you. Judgment sampling, quota sampling, and snowball sampling. See, in JAM the questions from the sampling is just like theoretical types. Okay, for example, in which sampling we use the kth unit after the random start, like this questions maybe came in the JAM examination. Okay, then after we will link estimation. Now this is a very important topic. Estimation in statistics. So what you mean by estimation? Okay, so estimation is about, so estimation means that you are estimating, you are calculating some value. Okay, for example, x, you are calculating the mean. So mean is what? Mean in estimated value. So estimation is about using sample data to estimate unknown population parameters. Okay, so use sample data. What is sample data? For example, you have the populations and from there you select some data, and that data you use for and that data you use for estimating the population parameters, because you don't have any time to to analyze all the populations data. Okay, in India there are many sample survey like NSSO, LASI, NFHS. These all are the sample survey data that estimate the health situations of the India by using the sample of 8 lakh 8 lakh samples. Okay, so from 140 crores there is a sample of 8 lakhs which give the estimate for over the India. You should, if you have time, just look upon the NFHS. It is a big sample survey, not big, large sample survey. Okay, so there is two types of estimation. First is point estimation, and the second is interval estimation. Okay, so first of all, point estimation. So what is point estimation? So a single numerical value used to estimate a population parameters. Okay, for example, suppose we have the population parameters and we have the point estimator. Okay, so we have mean, mu. This is your population parameter. So what you will estimate? You estimate sample mean, that is x bar. You have variance as a population parameter. What we will estimate? You will estimate sample variance. Okay. Now, properties of a good estimator. Now, so how will you know that this sample mean is a good good estimator of the population mean? So there are some properties, okay, that you should verify for the estimator to be a good estimator. That is, first is unbiased. We will discuss later on. It should be unbiased. Second, it should be consistent. It should be efficient. And is fourth, it should be sufficient. If estimator is satisfy all four property, then it is a good estimator. Now I will give you example that why should we use. Now, okay, let's suppose you have 1,000. Okay, so suppose like a real life example. So we know that the India population is 140 billion. Okay, now, and government want to know that how many how many people have toilets in their house. Okay, this is a type of question that asked in a survey of NFHS. So you have a population of 140 billion and government want to know that how many toilet are in the house of Indians. Okay, so what do you think that the government should have that much of time that they started asking the question from 140 billions, and from suppose 140 billions only 100 billions, because 40 billions we suppose are kid or children. Okay, so government has not that much time to just go and ask the question from the 100 billion, because it will be time consuming. It will like not cost efficient. It will take like very problem to ask from 100 billion. So what will we do? It will make the estimate from say 10 lakh. Okay, I think 10, yeah. So it will ask the question from the 10 lakh, which equally represent this 100 billion population. Okay, so these 10 lakhs will represent these 100 billion populations, and the estimate come from these will use to give the estimate to all over the India. Okay, so that's why need to be that if these 10 lakh, if the estimate come is unbiased, consistent, efficient and sufficient, and this estimator is a good estimator, and the estimate which this estimator is give is good. Okay, good. Then after we will come the another estimation, that is interval estimation. Okay. So instead of giving a single point estimates for x bar is 7, you give the estimate in a confidence and in a range. For example, you say that the my sample mean will lie in the range of 5 to 8. Okay, you say like my sample mean will lie in a range of 5 to 8 or 5 to 10. So this is interval estimation. So let me write the definition. Instead of a single value, we give a range of values that is likely to contain the true parameter. Instead of the single value, we give a range of the values that likely to contain the true parameters. Okay, yep. So this is all about interval estimation, and it is all about point estimation. So when you see what we have completed, so see, we have completed the random sampling, we have completed sampling, we have completed the interval estimation. So these are just a theoretical topic. There is no any like conceptual or mathematical formula, so that it is not take that much of time. So from now, from properties of estimation, sampling distribution, central limit theorem, so these are mathematical topic as well. Okay, so let's start the property of properties, or not properties, let's say characteristics of estimators. Okay, so what are the characteristics of an estimator? Unbiasedness, consistency, efficiency, sufficiency. Okay, so we will see each term in detail, because sometimes the question can be asked from the unbiased, like how will you calculate the unbiasedness, or is the estimator is consistent, or is the estimator is sufficient, etc. Okay, so we start with unbiasedness. Okay, so an estimator TN is said to be an unbiased estimator of if expectation of for all theta belong to the, this is your parametric space where your parameter is valid. Okay, now this is unbiased, and what if expectation of Tn is greater than phi theta? Then your Tn is said to be positively biased, or if phi theta, then Tn is said to be negatively biased. Okay, you have to take the expectation of the estimator, and if it is equal to the population's parameter, then it is a unbiased estimator. Okay, let me show with an example. Okay, example, let x1 x2 dot 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 xn is a random sample from a normal population n mu1. So this is your population. Okay, and in from this population you have draw a random sample x1 x2 xn. Okay, so we have to show that your our estimator 1 upon n sigma xi squared is an unbiased estimator of mu square plus 1. Okay, so this is our estimator, and we have to show that it is an unbiased estimator of mu square plus 1. Okay, so let's see how will we solve it. So random sample is given, normal population is given. Okay, so what is the mean of this normal population? So the mean of x is mu, it is given here. Okay, and what is the x squared? It is nothing but variance of x plus expectation of x whole square, that is equal to 1 plus mu square. Then expectation of t is equal to, now see, expectation of 1 upon n sigma xi square n I is equal to 1. Now 1 upon n we can take it outside, square. Okay, now take the summation outside. Okay, now what is the xi square here? This, just write it. And how many times you have to write it? 1 plus mu square, 1 plus mu square, 1 plus mu square to the n times. So we have to multiply it by n to 1 cut, it is 1 plus mu square. So it come to this Yeah, it is equal to the unbiased estimator. So T is equal to 1 upon n sigma xi square is and unbiased estimator of plus 1. Okay. Only you have to take the expectation. If it is equal to the given population parameter, then it is your unbiased estimator. Okay. Now we go for the next property. And that is consistency. So what is consistency? And estimator Tn is equal to T x1 x2 dot 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 xn based on a random sample of size n is said to be consistent estimator phi t, where theta belong to the parametric space, if Tn converges to y theta in probability. What does it mean? It's mean if y theta as n tends to infinity. Okay. Okay, let me define in some other language, in easy language. Tn is a consistent estimator of phi theta if for every silent greater than 0 there exists a positive integer n greater than m such that Tn minus phi t as n, or minus n. Okay, so this is the formula for your consistent estimator. We will see some examples so that it will be more clear to you all. Okay, so there is some of the properties which is also invariant, that is invariance property of consistent estimators. Okay, so what does it mean? I will only write the theorem, the proof is not important for your examination. If Tn is a consistent estimator of phi theta, it is given that the Tn is consistent estimator, you don't have to prove it here, and theta is a continuous function of gamma theta, then is a consistent estimator of theta. What does that mean? For example, you have an estimator that is Tn and it is consistent estimator. Okay, and it's this yt, and this yt is a continuous function. Okay, continuous function. So if it is a continuous function, then this phi consistent estimator is also the consistent estimator of this theta. Okay, now there is one important more, that is sufficient condition for sufficient condition for consistency. Let Tn be a sequence of estimator such that for all theta belong to parametric space, if expectation of Tn is equal to gamma theta as n tends to infinity, and the second is variance of theta Tn is equal to 0 as n tends to infinity, then Tn is a consistent estimator of phi theta. Okay, so if Tn is a sequence of estimator, okay, if you take the expectation and it is unbiased, and you take the variance of that estimator and it is become 0 as n tends to infinity, then T is a consistent estimator. You can mostly use this, and this is easy also. Okay, so let's see some examples so you will be more clear on this. Okay, so example, prove that in sampling from a normal mu sigma squared population, sample mean is a consistent estimator of mu. Okay, so here you have to show that it is a population and a sample mean is your estimator and it is a consistent estimator. Okay, so let's see the proof. So given population is normal mu sigma square, so and the sample mean, so sample mean is what? The sample mean is also normally distributed as normal mu sigma square by n. We have discussed this in the continuous probability density function. Okay, so what will be the expectation of x bar? So expectation of x bar is mu, and what is the variance of x bar? So variance of x bar is sigma square by n. So from this theorem, sufficient condition for consistency Statistic. Expectation of x bar is equal to mu as n tends to infinity. Variance of x bar is equal to 0 as n tends to infinity, because as n tends to infinity this becomes 0. Okay, so x bar is a consistent estimator of mu. Okay, see how easily from this theorem we prove that x bar is mu x bar is a consistent estimator for the mu. We will see one more example, and here if xn are random observation on a Bernoulli variate x taking the value 1 with probability p and value 0 with probability 1 minus p. So we have to show that sigma xi upon n
powering on
xi upon n is a consistent estimator of you will know why I take this example, okay, because it will contain all the concept that we have covered till now for the consistent estimator. Okay, so solution. So we have given x1 x2 xn are IID Bernoulli variate with parameter p. Okay, so t is xi will follow binomial np, because we have discussed that if x follow Bernoulli then x follow binomial. Why? Because in Bernoulli we have only one trial. For example, if we toss a coin single times, then it will be head or tail. But what if we toss the coin for the 10 times, then it will follow the binomial. Okay, then what will be the expectation of t? So it will be equal to np, and what will be the variance of t? It will equal to np into 1 minus p. Okay, now what about the x bar? Okay, so x bar is what? 1 upon 10 sigma xi. Take the expectation here, 1 upon n into expectation of x I, that is 1 upon n into np. Why it is np? Let me more clear. 1 upon n into sigma expectation of x, that is 1 upon n into, so this is what, this is Bernoulli here, so p, that is np, that is p. Okay, and what was the variance of x bar? So variance of x bar is equal to variance of 1 upon n sigma xi, that is 1 upon n square into variance of sigma xi, that is 1 upon n square into npq, n cut, that is pq by n. Okay, it tends to 0 as n tends to infinity. As n tends to infinity, it will become 0. So since expectation of x bar is equal to xp, variance of x bar is equal to 0 as n tend to infinity, then x bar is a consistent estimator of P. Now we have proved this, but we have to prove this x bar upon n. Okay, that is we have to prove x bar into 1 by n x bar. Okay, now this being a polynomial in x bar and it is a continuous function of x bar. So this is a continuous function of x bar. So from theorem first, that is this one, invariance property, x bar into 1 minus x bar is a consistent estimator of p into 1 minus p. See, that's why I'm taking this example, because here is the property, here is the theorem of inconsistent estimator. You have all the concepts of the consistent estimator and the sufficient estimator, sufficient condition for the consistency, both topic cover in this question. So this is very easy. Okay, let me explain one more time. See, so x1, x2, x3 are given as a Bernoulli variate with parameter p. X follow the Bernoulli, then the sigma of x will follow the binomial np. So our estimator is t x1, x2, x3 dot n. So when we take the expectation of t, we will become the np, because now it's follow the binomial distribution, and the expectation of the binomial distribution is np, and the variance of the binomial distribution is np into 1 minus p. So when we take the x bar, that is why we have taken the x bar, because see here we have sigma xi upon n, that's why we have to take in the x bar. So when we take the expectation, we will get the p. When we take the variance, we will get pq divided by n, and when we use the sufficient condition for this consistency, we will find that when n is tends to infinity, then the variance will become 0. Since here what we have done, so here we have to show that x bar into 1 minus x bar is the consistent estimator. So here we see that it is a continuous function. So in examination, the function was not that much long, so you can check the continuous of that function. If it is continuous, then you don't have to prove all of this, just you have to use the invariance property and you will get the consistent estimator. For example, here p into 1 minus p is the consistent estimator for the x bar into 1 minus x bar. Okay, now we will see the third. And what is the third? That is efficient. It is the efficient estimator. Okay, so what is efficient estimator? Efficient estimator is like, if now suppose first discuss why we need the efficient estimator. For example, you have two estimator who's are unbiased, both are unbiased and both are consistent, and how will you decide that which estimator you have to check? For example, we have x1 and x2, both are unbiased, both are consistent. Then now I will ask, like, which estimator should you prefer? Then what you will decide? So we will use the efficient estimator. Okay, we'll see if two consistent estimator t1 t2 of a certain parameter theta, we have then variance of t1 is less than variance of t2 for all n, then t1 is more efficient than t2 for all sample sizes. Okay, So for example, you have the two consistent estimator T1 and T2. Okay, so we will take the variance of both the T1 and T2. If the variance of T1 is less than variance of T2, then we will prefer T1. Means we will prefer that estimator whose variance is less. Okay, and how will you calculate the efficiency? So we will calculate efficiency like this: V1 upon V2. Okay, and its range will, and E cannot exceed unity, that is, okay. Now if E is greater than 1, you will T2 is sufficient for theta. If E is less than 1, T1 is sufficient for theta. Okay, if E is equal to 1, then both are efficient. Okay, yep. And this V1 is nothing but it is variance of T1, it is variance of T2. Okay, let me solve one example here. Now random sample x1 x2, so it is a size 5 random sample. Okay, from a normal population mu. Okay, now we have 3 mu and sigma square. Okay, so we have 3 estimator. T1 is equal to x1 plus x2 plus dot 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 x5 divided by 5. We have the another estimator, that is x1 plus x2 by 2 plus x3, and we have the third estimator, that is 2x1 plus x2 plus lambda x3 divided by 3. Okay, now we have to see which is the efficient estimator. Okay, okay. Oh, sorry, I just write wrong. Plus lambda x3. Okay, and here where lambda is such that 3t is an 3t3 is an unbiased estimator of mu. Okay, so we have to give a reason the estimator is best. Which estimator is best? Okay, so let me explain the question one more time. So we have the 5 random samples. Okay, and we have the 3 three estimators. What is T1, T2 and T3, and in 3T we have the lambda, and the lambda is take that value so that the 3T is an unbiased estimator. Okay, so we know that it is a normal distribution, so mu x is equal to mu variance of x is equal to sigma square. Okay, now so take the expectation of first T1, that is expectation of x1 plus dot 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 x5 divided by 5, that is 5 mu divided by 5, that is mu. Okay, and what about the, then we take the second expectation of T2, that is expectation of x1 plus x2 plus x3 by 2, that is 2 mu plus mu, that is 2 mu, but here it is 2 mu, but the normal distribution has mu, so T2 is a biased estimator. T3 expectation of 2x1 plus x2 plus lambda x3 by 3, that is 2 mu plus lambda mu by 3 is equal to mu, because it is given that it is an unbiased estimator. So just multiply that side, we have 2 mu plus lambda mu is equal to 3 mu. Take the 2 mu on that side, we have mu cut. So lambda is equal to here 0. What we have the lambda? 0. Okay. Now take the variance. So from the expectation we know that T2 is not an unbiased estimator, T1 is unbiased and T3 is unbiased. Okay. So variance of T1 is what? Variance of x1 plus x2 plus dot x5 divided by 5, that is 1 upon 25 into sigma square sorry 5 sigma square, that is 1 upon 5 sigma square. Variance of T2 is, you will get 3 by 2 sigma square, and variance of T3 you will get 5 by 9 sigma square. Okay, so take the comparison. Okay, so you will find that T1 is variance of T1 is a least, because here will see it is 1.5 sigma square, here you will see 5 by 9, but here is 1 by 5. So variance of T1 is the least, so T1 is a best estimator. So see, that's why we use the efficient estimator. Okay, there is a one definition that is known as minimum variance unbiased estimators. Okay, what did it mean? If a statistics T, that is T of x1 x2 xn, based on a sample size n, such that these are some conditions: T is unbiased for theta for all theta belong to parametric space. Second is it has the smallest variance among the class of all unbiased estimator of gamma theta, then T is called MVUE of gamma theta. Okay, let me write. So T is E of gamma theta if expectation of T is equal to phi theta for all theta belong to parametric space, and variance of theta T is less than or equal to variance of theta all other estimator for all theta up to theta. Okay, so what does it mean? So see, it's mean like we have to find the minimum variance unbiased estimator, means that the estimator will have the minimum variance. So what we have to do, we have the statistics. If T is unbiased, we have that statistics on the sample size n, and T is unbiased, and T is unbiased for the gamma theta. Okay, and t is the smallest variance among all the estimator. If these two conditions are fulfilled, that t is an unwise estimator and it has the smallest variance among all the unwise estimator, then your t is that MVUE of the phi theta. So this is known as a minimum variance unbiased estimator. And we have the last property of the properties of estimator. After that I will last property, that is sufficiency. So what is sufficiency? An estimator is said to be sufficient for a parameter if it contain all information in the sample regarding the parameter. Okay. So let me write, if t xn is an estimator of a parameter theta, based on a sample x1, x2, xn of size n from the population with density fx theta such that conditional distribution of x1, x2, xn given t is independent of theta, then t is sufficient estimator for theta. Okay, I know that this is linear very confusing, so I will take the help of examples and we will solve it. Okay, first of all I should recall this. So given if t is an estimator of the parameter theta, okay, based on the sample, okay, such that conditional distribution of x1, x2, xn given t, this is important, is independent of theta. If we take the conditional distribution like this, and it should be independent of theta, then we say that t is sufficient estimator. Okay, let me take the example. Okay, see, let x1, x2 be a xn be a random sample from a Bernoulli population with parameter p. Okay, So we have a Bernoulli population, that is 1 with probability p, or 0 with probability 1 minus p. Okay, so what is the estimator? So our estimator will be t xn, that is equal to xn plus xn, that will follow binomial np. Okay, so what is the probability of t is equal to k, that is nk pk into 1 minus p n minus k, where k is 0 1 2 to 2 n. Okay, now we have to find the conditional distribution, that is probability of x1 x2 xn given t is equal to k. That is what? Probability of x1 x2 x3 xn t is equal to k. Probability of t is equal to k. So this is a conditional distribution, and we can write conditional distribution in this way. So what we will do, if when we solve it, what we'll get? We get pk into 1 minus p n minus k divided by nk pk into 1 minus p n minus k. Okay, see, because x1 x2 dot 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 xn we have pk, and for that we have 1 minus p nk, and when we just cross it, and we will get 1 upon nk, and we will see that this is independent of p. So t sigma I is equal to 1 xi is sufficient for p. Okay, let me see some another example. There is one important topic, that is factorization theorem. Okay, this will also help you to solve the sufficient statistics problem. Okay, so what does your statement mean? If t is equal to tx is sufficient for theta if and only if the joint density function L of the sample values can be expressed in the form g theta tx into hx. Okay, where it is depend on theta and independent of theta. Okay, here you have to just write the joint distribution function in the form of this, where your g theta will be the function that contain the parameter, and hx should be independent. Okay, let me solve one question so that it will become easier. Okay, question: xn be a random sample from a population with, this time I will not take the normal distribution case. Okay, if x theta is equal to theta x theta minus 1. Okay, and we have to show that pi n I is equal to 1, xi is sufficient for theta. Okay, solution. Okay, so we have the random sample, we have this PDF. Okay, so we will write the joint distribution, that is phi n equal to 1 fxi theta. We will write for all the samples that we have taken this phi here, that is theta n into 1 xi theta minus 1. Okay, now theta n into phi n I is equal to 1 xi theta into 1 upon phi xi. We can write this in a form of, yes, we will write. So we will see here, this is written in a form of g theta into x1 x2 xn, where this, where g theta t is equal to theta n, phi n I is equal to 1 xi theta, and h x1 x2 xn is 1 upon phi xi. So t1 is sufficient estimator of for theta. Okay, so by this you need here is to write the joint PDF, and while writing the joint PDF you have to break this in a form of g t theta and hx1, where it is dependent on theta and it is independent of theta, and you will get the sufficient estimator. If you write in this form, then you will get the sufficient estimator, otherwise it will not sufficient estimator. Okay, so this is from my side. Thank you. In the next class we will see about the, so in the next class we will see the remaining things, that is we have completed this. In the next class we will see the sampling distribution, confidence interval, central limit theorem, law of large number, and estimating the population parameters. And by that your mathematical statistics portion is also completed, and we will solve some PYQ questions on these mathematical statistics topic. Okay, so thank you.
जेएनयू के बारे में सबसे बेस्ट चीज आपको क्या लगता है? आने वाले सीयूईटी एस्पिरेंट्स के लिए आप क्या बताना चाहते हैं? कुछ सजेशन तो आप बच्चों को क्या बताना चाहते हैं जो कंफ्यूज रहते हैं, डीएससी आना चाहिए या जेएनयू आना चाहिए? ये आप बताइए। बच्चे ये जानना चाहते हैं जेएनयू में मेरा एडमिशन हो गया, उसके बाद मुझे हॉस्टल मिलेगा या ना मिलेगा? आने वाले सीयूईटी एस्पिरेंट्स जो भी है, जो प्रिपरेशन कर रहे हैं और आना चाहते हैं जेएनयू, डीएससी, आईआईटी, तो उनके लिए क्या सजेशन देना चाहते हैं? वो किस एरिया में ऊपर उनका